class, let's take a look at the Chapter 9, 10 review packet here. There's 6 problems on here, so what I decided to do was to have them pre-written out and just kind of go through the highlights of them. Pick the ones that you want to take a look at. I would actually take a look at the keys, check them out. If there's ones you don't understand, then listen to each of the problems. I'm hoping that doing it this way causes the video only to be about 30 to 40 minutes long, because I know these problems each take about 10 to 15 minutes just to do by hand. All right, so let's take a look at number 1. It says economics often track employment trends by measuring the proportion of people who are underemployed, meaning they are either underemployed or would like to work full-time but are only working part-time. In the summer of 2010, 18.5% of Americans were underemployed. The mayor of Vicksburg wants to show that voters in the situation is not as bad as his own town as it is in the rest of the country. His staff takes a simple random sample of 300 Vicksburg residents and finds that 48 of them are underemployed. Do you have convincing evidence that the proportion of underemployed in Vicksburg is lower than elsewhere in the country? So when I'm deciding what type of test here, I only have one sample of data going on here. I'm just going to kind of highlight everything in pink. I have one sample of 300 where 48 of them are considered underemployed. Notice how it's asking us, does it give us convincing evidence? So I'm thinking a test on a proportion, okay, and where that proportion is equal to that of the population. So hence why my null hypothesis is going to say the true proportion is equal to 0.185, the true proportion of Vicksburg's residents who are underemployed. The alternative will say less than 0.815. So right now I know that I'm doing a one sample z-test for a population proportion at 5% significance level. That significance level is not given, so I assume 5%. So I go through my conditions, random, normal, independent. Okay, so these should go pretty quick. It is random, simple random sample of 300 Vicksburg residents was taken. Is it normal? Okay, so what I need to do is take a look at here. Remember, it's P of the null hypothesis. So where I'm actually getting this from is, I know it says 55.5, is I actually have to go 0.185 times 300. Okay, that gives me the 55.5, and then this is 1 minus 0.185 times 300. That's where the 244.5 is coming from. Need to check, is the population greater than 10 times the sample? So is our population greater than 3,000? So in this case, yeah, we would assume there's at least 3,000 residents in Vicksburg. All right, so now let's calculate out our z-score and our p-value. So again, excuse me, our sample proportion was 48 out of 300. So their underemployed rate is at 16%. Question is this significantly different? So you take your sample, 0.16, minus the proportion of the null, 0.158. Then divide it by the standard deviation of the null hypothesis. So 0.185, 0.815, this is 1 minus 0.185 divided by 300. This gives me negative 1.12. Just to show you that, 0.16 minus 0.185, that's negative 0.025. Okay, so the standard deviation, okay, so I could just say divided by the standard deviation of 0.185 times 0.815 divided by 300, so long as that's all under the square root. Okay, you can see negative 1.15. I only went out 2 decimal places, so if you went out 3, your p-value will be slightly different. Remember that your p-value, my p-values don't have to be exact. They should be relatively close. I'll look for your work. So again, to get this p-value, I know it's not written here, but we would go normal CDF from negative 99 to negative 1.12. So I'm just doing that right in my calculator. Second bars, normal CDF, negative 99 to negative 1.12. So just to show you, that's where that p-value is actually coming from. Okay? So when I look at this p-value, I like to interpret it in the context of the problem. So I would look for that on the test, on our test. But on the AP exam, it's something you wouldn't necessarily have to do. So again, what does the p-value mean? Basically means our result or one more extreme is going to happen that percentage of the time if the null hypothesis was true. So I just put it in context. Our result or one more extreme, less than 0.16, would occur 13.14% of the time if the true proportion was 0.185. Okay, so what does that mean? Since our p-value is greater than 5%, we fail to reject our null hypothesis. That is, the mayor doesn't have convincing evidence that the proportion of underemployed in Vicksburg is lower than elsewhere in the country. Even though it was lower, it's not significantly lower. At least we don't have statistical evidence to support it. Okay? All right, so that takes care of the first problem. All right, going on to number 2. It says when the manufacturing process is working properly, never-ready batteries have lifetimes that follow a slightly right-skewed distribution with a mean of 7 hours. A quality control supervisor selects a simple random sample of 50 batteries every hour and measures the lifetime of each. During one particular hour, the supervisor collected a sample of 50 batteries that had a mean of 6.92 hours and a standard deviation of 0.27 hours. She is convinced that the mean lifetime of those batteries produced is less than 7 hours at the 5% significance level. Okay? So notice how in here they're giving you means and the standard deviation right away. Right away, I'm thinking this is a one sample mean type of test. But of course, in question A, they ask you to describe the type 1 and type 2 error for this situation and the consequences of this. So notice how it says the batteries will be discarded. So remember, type 1 error is rejecting the null hypothesis when in fact you shouldn't have. That's like saying the mean battery life or lifetime batteries is less than 7 hours when in fact it was actually meeting it. Okay? So what's the consequence? She's throwing away the good batteries. The type 2 error is failing to reject the null hypothesis when you should have. She now is saying the batteries were at 7 hours when in fact they're not. The company is now going to be producing batteries that are less than 7 hours than advertised. That could cause them to lose customers or potentially do some sort of recall. They're putting out bad product out into the population. So now, part B actually asks you to do the 4-step process. So, again, state plan do conclude. So our state, we'd say that the mean is 7. We're saying the alternative is less than 7. Mu is the mean lifetime of the batteries that are being produced. Okay? We're going to do a one sample t-test for mean, because t and mean go together at the 5% significance level. Is it random? Yes. The inspector takes a simple random sample of 50 batteries. Normal, okay? We don't know the population. We don't know if the population distribution is normal. In fact, it is stated in the problem that it is slightly skewed to the right. However, since our sample size is 50, this is where central limit theorem comes to the rescue, and it saves our day. Okay? So then we check to see if it's independent. Is our population greater than 10 times our sample? Or is the company producing at least 500 batteries? Absolutely. They're probably producing thousands of batteries. All right. So now we need to calculate out the t statistic and the p-value. So t statistic is found by taking your sample mean divided by, or minus the mean of the null, divided by the standard deviation over the square root of the sample size. So again, this is really the standard deviation of the sampling distribution. Okay? So 6.92 was our sample mean. Okay? We wanted 7. So the question is this sample mean significantly low enough to say, these batteries are bad? So our standard deviation was 0.27. Our sample size was 50, so the square root of 50. So just to show you where this p-value is coming from, 6.92 minus 7, so we get negative 0.08. Divided by, I have to put this in parentheses, otherwise, if I'm going to do it all at once, otherwise you are going to get completely, whoops, I got to delete that little part and get that on the outside. Otherwise, you're going to get a completely different p-value. So this one I decided, I guess, to go 3. So our degrees of freedom in this case, remember, degrees of freedom is sample size minus 1. 50 minus 1 is 49. So that's where that's coming from. So plug this into your calculator, and you should get a p-value about 0.0207. So, again, we interpret what that means in the context of the problem. So our result, or one more extreme, meaning less than 6.92 hours, would only occur 2.07% of the time if the true mean of the batteries was 7 hours. So again, since our p-value is less than 5%, we reject the null hypothesis, meaning we have statistical evidence that the mean lifetime of the batteries being produced at this particular time was less than 7 hours. So the inspector should reject this batch of batteries. So if she's making that mistake, she destroyed some good batteries. But in this case, that's what she needs to do. I was just kind of talking about what the error, if she was making one, would be. All right, 2 problems now. 4 to go. Wow. All right. So number 3 says, nicotine patches are often used to help smokers quit. Does giving medicine to fight depression also help? A randomized double-blind experiment, wow, chapter 4 terms right there, assigned 244 smokers to receive a nicotine patch and another 245 to receive both a patch and an antidepressant drug, bupropion, if that's how you pronounce it. After a year, 40 subjects in the nicotine patch group had abstained from smoking, while 87 in the patch plus the drug group had abstained. So this one says, construct and interpret a 99% confidence interval. Wow. For the difference in the proportion, so that's telling you what type of interval you're doing, of smokers who abstain when using bupropion and a nicotine patch, and the proportion who abstain when only using the patch. Okay? So, state plan do conclude. So we state, what type of interval we're trying to find. So I just want to make sure I'm saying 99% confidence interval for the difference between the proportions of those who abstain when using both the drug and the patch versus those who are just using the patch. So I'm doing drug and patch minus just the patch. So I define both of those, P of B and P of P. P of both versus P of just the patch. So I've defined those, so knowing which one is which. Okay. So now, that took care of the state. The plan will say we're going to do a 2-sample Z confidence interval for the difference of the proportion. Okay. So we're doing a confidence interval, no level of significance needed. So is it done randomly? Yes, subjects were randomly assigned to one of the 2 groups. Sweet. Was it independent? Yes, it's an experiment. Okay. Ooh, I did this out of order. It's an experiment, so it seems reasonable that one subject sustaining from another group will not impact the subject of another group. We really don't need to check to see if the population is greater than 10 times in this particular case. So now, normal is the number of people that are succeeding and not succeeding all greater than or equal to 10. So in the both group, we had 87 successes. Okay? This number right here, 158, is coming from 245 minus the number of successes. This is how many people aren't. Likewise, in the second group, just using the patch, 40 people were successful. This number was coming from 244 minus 40. Since all of those are greater than or equal to 10, our distribution is considered approximately normal. So now we need to calculate out our confidence interval. So here's our two respective sample proportions. So when doing both, it's 35%. When just doing the patch, it was about 16%. So that we take the difference between the two proportions plus or minus z star. So a 99% confidence interval, if we look it up right at the table, should be 2.576. So to find the standard deviation, I plug in the respective values for each of them. So I get the difference. So just to show you where these two numbers are coming from. So 0.355 minus 0.164. That tells you that the difference between the two proportions is almost 19%, plus or minus. What's my standard error? So I can go standard deviation of 0.355 times 0.645 divided by 245 plus 0.164 times 0.836 divided by 244. Calculate that out. Now that's the standard error. I have to times that by my z-score, how many standard deviations I need to be away. So 0.0996 or about 0.10. So if I add and subtract that, I get my confidence interval. So remember, how do we interpret a confidence interval? Well, we would say we are blank percent, 99% confident that the interval from lower bound, upper bound captures the true difference of what? Context of the problem. The proportion of smokers using both the drug and the patch who abstain versus the proportion of smokers who just use the patch that abstain. So part B basically gets you to think about how you could use the confidence interval to see if there's actually significance difference. So in B it says, based on only this interval, do you think that the difference in proportion of abstaining smokers is significant? Justify your answer. In this particular case, yeah, if there was no difference, okay, we would be saying, okay, that P of both would equal P of just the patch, okay? We're trying to show evidence that they're not equal to each other. If they're not equal to each other, this would be like saying that their difference was equal to 0 versus not equal to 0. So since 0 is not in our interval, it actually gives us evidence to say that there is a significant difference, and it's at the 1% level because 100% minus 99% leaves us 1% in the rejection region. All right, continuing on, number 4. So it says, just before the presidential election back in November of 2008, a local newspaper conducted a poll of residents of medium-sized cities and found that 120 out of a simple random sample of 250 men intended to vote for Obama, and 132 out of a simple random sample of 240 women intended to vote for Obama. Is this convincing evidence that there was a greater difference in the Obama support in this city? Support your conclusion with a test of significance, meaning difference in gender, basically. So we're going to define P of M and P of F being the proportion of men versus proportion of women intending to vote for Obama in the city in the 2008 election. So the null hypothesis, another way of saying it is we would say the proportion of men equals the proportion of women. Another way we could say is the proportion of men doesn't equal the proportion of women. However, if you move these over to the other side, that's where the subtraction comes into play. And this helps me determine what type of test. I have two samples, and they're both proportions, hence why I'm doing a difference between two proportion tests. So a two sample Z test for a difference of proportion at the 5% significance level. They actually say that level right there. Right? So random, normal, independent. So random, yes, we have two simple random samples, one of 250 men, the other 240 women. Are the number of people that said that they are not going to support them all greater than 10? 120 men said yes, 130 men said no. 132 women said yes, 108 women said no. Remember, these two add up to 250. These two will add up to the 240 women. Are they independent? We do have two independent samples of men and women, and both samples are, or both populations should be greater than the sample. We could easily have 2,500 men and 2,400 women in this city voting in the election. Okay? So now the question is there actually a difference in the proportion? So the proportion of men that said was 0.48. The proportion of women that said was 0.55. So I got those just by dividing. However, I got to look at the combined. So no matter what gender they were, 0.514, or about 51.4% of people in general were going to support Obama in 2008. So we want to know, is this difference between these two proportions significant when in the general population it's 51.4%. So you calculate out Z, the difference between the two proportions. So 0.48 minus 0.55, that's the negative 0.07. And then you do the standard deviation of the combined. For time's sake wise, enter that in the calculator. Make sure, okay, you have this all under the square root. You get 0.0452. You get a Z-score of negative 1.55. So when I do the p-value, I like to go normal CDF. It's not written here, so I'm going to write it here. From negative 99 to negative 1.55. That's where this 0.0606 is coming from. So just to show you that, normal CDF, okay, negative infinity to negative 1.55. Paste that in there, 0.0606. Now it's got to be double, so my p-value is 0.1212. So what does that mean? Well, a result more extreme, meaning the proportions will differ more, will occur 12.12% of the time if there was no difference in the proportion of men versus women in the city that support or intend to vote for Obama. Since our p-value is greater than it, we fail to reject. Again, anytime it's greater, we fail to reject, meaning we do not have convincing evidence that one gender intends to vote for Obama more, okay, than the other. Okay? All right. Woo! 2/3 of the way done. 2 more to go. All right, so Jordan's cat, Fern, is a finicky eater. Jordan is trying to determine which of the two brands of canned food Fern prefers, Tabbycat or Chow Lion. For 2 months, she flips a coin each day and decides which of the two food to feed Fern and weighs how much Fern eats in grams. Here is the data. Well, this is kind of nice because notice how both these values are greater than 30. And they already did the sample standard deviations and everything, so we don't have to calculate anything major up. So it says construct and interpret a 99% confidence interval for the difference in mean. Wow, they're making this pretty easy for us here. So it tells us what type of confidence interval. So I'm going to define what interval I'm finding in the context of the problem. So again, we say we want to find a 99% confidence interval for the true mean difference in mean amount of cat food Fern eats when given Tabbycat versus Chow Lion. I'm defining mean of T as Tabbycat, the mean amount he eats, and mean of C as the mean amount of Chow Lion Fern is eating. Okay. So what type of test? Since we're talking about means, 2-sample t-test. Okay, for the difference of the means. They didn't give us a level of, it's a confidence interval, so I don't need a level of significance. Sorry. Me, myself. So hopefully I didn't say t-test, I said t-confidence interval. So if I accidentally said test there, I meant confidence interval. So I get so used to doing tests here. So random, normal, independent. So yes, is it random? The days Fern was given the food was randomly assigned by coin flip. Is it normal? Since they're both greater than 30, okay, normal conditions are met according to the central limit theorem. Independent, since this is an experiment, both sets of days can be viewed as independent and reasonable to assume because fur ate each day has no, what he eats one day has no impact on what he eats the other day. All right, so now let's calculate out our value here. So I take the difference between the mean plus or minus the t-star score times the standard error of the difference between two means. So now my degrees of freedom, okay, since I would technically go 31 minus 1 and 30 minus 1, I have 30 and 29. So the degrees of freedom we want to use is actually 29 here, okay? So you can look that one up right up at the chart, or if you think about inverse norm, so I'm sorry, not inverse norm, inverse t, we could go 0.995 and a degrees of freedom of 29. If I paste that in there, that's another way I'm getting this is by going inverse t, a 0.995, and degrees of freedom of 29. So I take a look at the difference between, so looking at this, he's eating about 3.1 more grams of Tabacat on average than he is of Chow Lion, I think it was. Sorry, I don't know why this all of a sudden became a M. That should be a C, so I apologize that I'm kind of changing up the symbols I use there. So it was called Chow Lion, wasn't it? Yeah. So those are always these small mistakes I even find in my keys. So if you calculate this part out and multiply it out, if you just trust me, it ends up being 2.88. So plug it in your calculator and just double check. I sometimes will do this part first and then multiply it. So if I add and subtract it, the mean difference between the two is somewhere between 0.22 and 5.8 or 98 grams. So to interpret it, we are 99% confident, blank percent confident, 99, that the interval from 0.22 grams to 5.98 grams captures the true mean difference in the mean amount of food Fern eats, Tabacat versus Chow Lion. So if you're actually doing a test, if you were trying to show that it was statistically significant, yeah, we would actually have statistical evidence that Fur prefer or eats more Tabacat than Chow Lion, since 0 is not included in this interval. You're not asked that, but just wanted to point that out. All right, very last one. Woo! This one takes probably the longest to do. So it says, Mr. Bartz wants to see if flipping the classroom in AP Stats class is a better method of teaching than the traditional method. In order to do his experiment, Mr. Bartz randomly assigns 25 of his students to flipping the classroom method and 27 of his students to the traditional method. After teaching for 1 week, all students take the same exam and the mean test scores of each class will be compared. The results of the exams are noted. Boy, Mr. Bartz, why couldn't you have put over 30 in each class? That would have been so much better, but of course I did. Of course I needed to do one that involved graphing, which you'll come to see is like your least favorite thing to do with these problems. Okay? So one of the things I did was I put this in list 1 and list 2 and did one variable statistics on each, so I could get the flipping the classroom data and the traditional data, the mean and standard deviation of test scores. So I want to see, is there statistical evidence that flipping the classroom is better than the regular traditional teaching method at the 5% significance level? So I'm saying the difference in their mean scores is 0 versus that the difference between the two scores is greater than 0. Because I'm doing flipping the classroom minus traditional. If you flip these, then this greater than becomes a less than. Notice how I've defined mean of the flipping, mean of the traditional. So again, the type of test you're doing is a two-sample t-test for the difference between two means. They do give you a significance level of 5%. Normal. Fortunately, they were both less than 30, so I had to graph both of them. So I did graph flipping the classroom and traditional classroom. In fact, what I did was I actually did a modified box plot above both of them just to check, just to make sure there weren't any outliers. So since both graphs and box plots for each showed no outliers, very little skewness, we are safe to assume our distribution will be normal. Excuse me. So now I calculate out the t-statistic, the difference between their means minus the difference of the null, which is always 0, over its standard error. So the difference between the two scores was a mean difference of 3.16. Okay? The standard error, the standard deviation, ended up being 2.675, which gives you a t-statistic of 1.18 degrees of freedom. We take the smaller of the two, so this really should be 24 because we go 27 minus 1, 25 minus 1, so 26 versus 24. So we calculate out our t-statistic, 1.18 to infinity, degrees of freedom of 24. So our value is 0.1248. So our result, or one more extreme, would occur. All right, sorry, I actually had to stop the video. So just to go over the conclusion again, here's our p-value, 0.1248. So basically that's the probability that our result, or one more extreme, okay, that this difference would even be bigger, okay, if there was no difference between the scores in the first place. So this is happening 12.48% of the time. So since our p-value is greater than alpha, we fail to reject the null hypothesis. That is, we do not have statistic evidence that flipping the classroom is a better method of teaching than that of our traditional method. All right, I hope at least going over it this way worked well for you. If not, just email me questions. Talk to you later.